Okay, now, welcome back. Now that we have just have the model which has converged, and it shows that that's the right time right now to just draw some posteriors. I'm just going to call that posterior model B. It's going to be the name of the object, which I'm just going to extract. And extract is from, I should say, the RStan package. And I'm just going to call that the model B. And as long as I'm just looking for all, I should say, the estimates, all the rows from, I should say, for a model, I do not define the parse. And execute the line. And I have an object now created. Let me... Now it's fine now. And now look at that. And now I have an object. This is called posterior model B. And if you click on it, you will see that it's a big data set which contains 7 elements. The first element of our data sets, you see that we have some, I should say, some rows for the U, which it's going to be the parameters of our interest. You see that it's 8,000 by 3 matrix, which it means that if you look into that, the rows which we have is going to be essentially for U1, representing, I should say, the converted random intercept. U2, which is going to be the second column, represents the demented random intercepts. And U3, which represents the non-demented random intercepts. We have 8,000 rows, which it means that we have 8,000 rows from our posterior distribution, and each row represents one possible value for each U1, U2, and U3. And as you remember from the previous course, the best way to just find what is the best value for each U1 or U2 or U3 is using the Monte Carlo estimation by taking the mean of our model. And that's the thing which I'm just going to do. I'm just going to come here, take a look, posterior model B. If I'm just going to use the $sign, get the attribute of the U, and if I do that, you will see that I get a huge and enormous number of the values which comes here, which is going to be, as you notice, that it's going to be 8,000 because we had 4,000 iterations. Half of it is going to be gone as the warm-up. Then we have 2,000 iterations. Then multiplied to 4 chains, it becomes 8,000. Then we had 8,000, I should say, those from our posterior distribution. And now you will see that. In that case, imagine that we are looking for, essentially, for example, the random intercepts for our model A. In that case, we have to define a dimension for the U. And you're looking for the U1. If you go back again to the posterior model B, you see that for the U, we have essentially 8,000 times 3. Then it means that if I just come here, just show that all the, I should say, all the rows, and I just put number 1, and I execute that there, you see that all the elements which I get, essentially, it represents all 8,000 values, and the estimate which comes from the rows from the posterior distribution for the random intercepts of the U1, which as we just assumed, U1 represents to the converted cases. Then we see that then, if I just want to see what is the best estimates by using the Monte Carlo, I'm just going to take the mean of these elements. And I'm just going to execute the line. We see that the mean is going to be a minus 0.0065, something like that. And that's why I'm just going to call that also, I'm just going to call that B naught for, let's say, I'm just going to, it's going to be this value. And also, we can do the second thing. We can just also come to just take a look at the posterior for model B. I'm just going to extract the value of my interest, which is going to be the mu. And I'm just going to get the case for a demented case. For the demented case, I know that I designed it to be, I should say initially when I assigned a value to that categorical variable to be number 2, then I take all those H rows and I just focus that on column number 2 and I'm just going to execute that. We see all the values for the random intercepts, for the demented cases. We have 8,000 values because we draw 8,000 times from our posterior distribution. And if I take the mean from it, we see that we get that mean, which is essentially, it shows that the random intercepts for our value. I can call that B0 for demented. And I'm just going to store that into an object like that. And also similarly, I can just go ahead with the same logic. I just go to the posterior for model B. I'm just going to take a look in the U, and I'm just going to only check the U for, let's say, the non-demented case, which is going to be number 3. I'm just going to, before executing that, I'm just going to take the mean of it, because that's the thing which we did, to take the mean of 8,000 possible values for the random case, for the random intercepts, for the non-demented cases, and I'm just going to call that B0 non-demented. And I'm just going to store that, execute the line. We see that, okay, we get one possible case for this one. And see how much is that? We can also execute this one. We see that it's going to be 0.01. And we see that now when we just visualize that, we see that the mean, which are random intercepts for the cases, which they are just going to be non-demented, we see that it stands above the other demented and the converted cases, which it shows that at the age of 60, the normalized whole brain volume of all in the groups for the cases that they are non-demented and they haven't been diagnosed with the Alzheimer, it's much bigger than the cases that they are demented and converted. That's the thing which we expected to have based on our knowledge from the scientific literatures, but also we showed that on the Bayesian analysis, which our computation, it's in, I should say, as you see, it's going to be somehow within the same thing as the scientific experiments. In order to visualize it, I'm just going to write a function. I'm just going to call that as an apply. I'm just going to apply the function. I'm just going to apply the function on my posterior model B. However, I'm just going to extract just only on the parameter of my interest, which is going to be the U. And with the second argument, you know that I'm just going to use that on the columns, because you remember the U, as I showed that to you, I'm just going to go back again to open the posterior for model B. You see that the U is a huge matrix. It has 8,000 rows and 3 columns. Each column 1, column 2, column 3, refers to different levels within the group. Column 1 with the converted cases, column 2 refers for the demented cases, and column number 3 refers to non-demented cases. And now, then as a result, I look at all the columns. That's why I choose assign number 2 as a second argument for the function apply. If I just wanted to look into the rows, I choose 1. If I look at the columns, I choose number 2. Now, the function which I'm just going to use is that I'm just going to use the quantile function. I'm just going to check for the quantiles, which it gets the first 25%, the median, and also the third quantile, 75%. And also, I'm just going to just check the probes, the probability which it's going to be referred to, which it shows also credible intervals. It's going to be a combination of, let's say, the 95% of my data, which is going to be essentially from 0 to 25. And also I show that 0.5, and also I show that 0.975. I'm going to execute that, and you see that the thing which I get here, as you see that at the console level, it shows that, okay, the credible intervals for each random variables for the random intercepts of all the groups. Column number 1 refers for the case that they are converted. Column number 2 refers for the case that they are demented. And column number 3 refers for the case that they are non-demented. And they have not been identified patients with the Alzheimer's disease. However, you see that the credible intervals has been assigned from 2.5% to 97.5%. It shows that the 95% credible interval, which it means that there is a probability of 95% that the random intercepts, for example, for the converted cases, falls within this interval, between minus 0.11 all the way to 0.077. And also the same story for the demented cases and the same story for the non-demented cases. You can say that, okay, there is, for all these cases, for all these levels within the group, we have 95% credible probability that the value of the random intercepts, which it shows that the normalized whole brain volume of them to fall within these intervals, from this line to from this interval. Okay, and now the thing we just want to do is that we just want to also visualize the thing that we had it before. I'm just going to assign a name to that. I'm just going to call this, let's say, I'm just going to call that group. Let's call that EFF, effective. Then we see that, okay, I store that object, the information into that information. And also, the other thing which I'm just going to do before I just go ahead to do the plotting, I'm just going to go over there and create a data frame of my data. In order to do that, I'm just going to just go ahead with the data, that frame. The thing which I have planned in mind, I just want to visualize the inferences which I just got from my, I should say, from the Monte Carlo estimation which I had in my model. For my data frame, I define an ID, and for the ID, I say that I'm just going to use the function unique to check for all the data, which is going to be the group. Then it searches for, in the data sets which I have, for whatever data it is, they just take it into the groups that it belongs to. And also, I'm just going to use the argument for the group, and I'm just going to choose that also the same thing for the group. Then it means that the plot is going to be done, the data frame is going to be done by within the group level. Then I have the lower interval. I'm going to define the lower interval to be, let's say, the group EFF, which I defined it before, but I'm looking for only the first column. The first column, remember, it was, I should say, I'm just going to get the first row, because you remember that the first row, it's going to be the lower interval, but the second first column, you see that this one shows the lower interval. It means that the first row, and I should say it's going to be one, and the rest of columns, it shows that the lower interval for the converted, non-converted, and demented. And also, I can talk about the median. The median is going to be essentially the same thing which I defined before. I'm going to call that the group EFF. However, it's going to be the second row. For the higher interval, it's going to be essentially the same thing. It's going to be again the group EFF. I know that I have to look at the third row, but all the columns. And I'm just going to execute the line. You see that I have the same thing. If you compare them, you see that these things are the same, but I call this one the lower interval. It becomes the up median, and it becomes the higher interval, and I have the group 1, group 2, and group 3. And I'm just going to call that, I'm just going to assign it a name. I'm just going to call that the data frame for the group. The same thing, we are just going to do that when we just go to the different stages for the Alzheimer. I'm just going to execute the line, and the line has been executed. Okay, and now I have the data frame, which now takes part, I should say, takes into account the, I should say, the lower intervals, the median, and the higher intervals of the estimates that I just got for the random intercept. Now, in order to plot that, I just wrote, in order to save time, I wrote the codes. For that, I just hide it here, that at the right time I can just use that, which is a function which I wrote it for the gplot2. You have to make sure that you have the ggplot2 library installed. Then when you have it installed, you can just go ahead and you can also find the codes in the thing which I have just shared that with you. To find the codes, I just use the ggplot in order to visualize the lower intervals, the median, and the higher intervals of the estimates which I had for the random intercepts for the variations between the groups. I'm just going to execute the code and see what is going to be the result that we're just going to get at the end. Okay, I executed the line, and we see that the plot has been created. I'm just going to zoom this. You see that based on the things that we have, at the horizontal, I should say, axis, you see that the ID which we have. ID number 1, again, refers that to the converted cases. ID number 2 refers to the not demented cases. And the ID number 3 refers to, I should say, non-demented cases. You see that when we look at the plots that we have just obtained, if we look at the dots which we have there, the dots which we have there represents essentially the mean value of the estimates that we had for the, I should say, for the normalized whole brain volume at the age of 60. At the model that we have, you see that the lowest value which we get, it refers for the ID number 2, which refers for the case that it was non-demented case. It shows that in our group, because of the variations that we have within the levels inside the group, it shows that the mean, which refers to, I should say, the mean of normalized whole brain volume of all participants in our study, shows that for the case ID number 2, which it refers to the demented cases, they obtained the lower level, I should say, of the cases. However, for the converted cases, then later is going to be, you see that the non-demented case, it's going to be a little bit above of the non-demented cases, and for the converted cases, we see that the level, I should say, the normalized whole brain volume is way above the rest of the two, and that's the thing which needs to be considered and to be investigated further, and what's the reason. But at this stage, we have been able to show that the normalized whole brain volume, because of the variations inside the group, if they are just going to be converted, non-converted, and converted, it's going to be different. And we see that difference right now when we just add one level of the hierarchy into our Bayesian analysis. That's the thing which we didn't see that in our model A. And in that case, you saw that the demented cases have at the age of 60, because they're random intercepts, it means that the normalized whole brain volume at the age of right 60. We see that those people who has been demented at the age of 60 in our analysis have the lower level, I should say, of the normalized whole brain volume, or they have the highest level of the brain atrophy. I should say at this stage, then we are done with our analysis of the hierarchy model of the Bayesian analysis with respect to the variations between the group level. Now, when we come back from the next tutorials, we are just going to add one more level of the hierarchy into our case, and to see that if we look into the case that if the persons in our groups, they have been demented, depending on what stage of the Alzheimer's they are in there, if they are mild or if they are severe or any other cases, what is going to be, I should say, the case of the thing that they have, the normalized whole brain volume. And also before that, we are just going to check if, even though with the case that we have at this level of the hierarchy, what is going to be the slope of the brain atrophy? Are they going to, for example, the cases of the demented, non-demented, and the demented case, they are just going to show the same level of, I should say, brain atrophy and the same rate of the brain atrophy. These are the questions that when we come back at the next tutorials, we're going to discuss and talk about them. Okay, I can't wait to see you on the next tutorial. Maybe we're going to talk about more interesting and more fascinating stuff using the hierarchical Bayesian models.